Okay, now you can do it.
Okay.
Okay, so here's the deal. For the first part of the experiment, for the Hooke's Law part, we're going to ignore the mass of the mass hanger. So we're going to have this on here, but we're not going to worry about the mass. And we can do that because we're interested for the first part in finding out how many newtons it takes to stretch the spring a certain amount. And what we're going to do is just take this length as the unstretched length. Now, I guess, should I write something on the board yet? Hooke's Law. And this man Hooke was quite an interesting fellow. He was a medical doctor, but he also did, experiments in a lot of physics, and he was quite the Renaissance man, this Hooke. So here's what he figured out, that the force a spring exerts on a mass is equal to the negative of a constant times however far the spring is stretched. Now, this gives you the force exerted by the spring and this is how much the spring is stretched. And then that's called the spring constant, K. Now, if you just pay attention to the magnitude, then you can say F equals KX. So that's what we're testing, or we're going to use this relationship to determine the K of the spring. And K, the spring constant, is measured in newtons per meter. And the amount of stretch is going to be, if this is the, we'll call that the equilibrium position. And then if we put more weight on it and it stretches down to this distance, then this is the X, the amount of stretch. I guess it's more appropriately a Y because it's a vertical stretch, but it's the difference between the two positions. Okay, that seems like it should be pretty straightforward. Now we're going to put from 100 grams to 500 grams on, and you're going to make two measurements, a position measurement, and then you're going to, actually that's one measurement, and then you're going to subtract to find the stretch. So here's what I'm going to recommend. I'm going to recommend that you make your original position. I'm going to make mine 100, but you could go the other way. I'm going to make it 100 centimeters or 1 meter. I'm going to try to, maybe it'd be easier to lower this one. So my original position is going to be 1.0. And actually you're going to want it to 1.000. Okay, I'm just going to call that in. You don't need to watch me make adjustments endlessly here. That probably changed it, just tightening that. Yeah, I'm off by some fraction of a centimeter. Okay, so my original position is 1. This is the M in grams. This is the M in kilograms. So first we're going to put 100 on, and that's 0.1. And position in meters. And then stretch, do we call it stretch? Yep, stretch in meters. So for the 100, I'm just going to put a 100 gram mass on here. You can see it stretched it. And now I'm going to get the new position. And my new position is, I hope they won't stay on. Oh, I'm going to call it 88.3. There was a little bit of oscillation. So 88.3 is 0.883. And I'm thinking yours shouldn't be way different from this. Your numbers should be, you know, within 5 centimeters of mine, maybe. Because I think all the springs are pretty close to the same spring constant. Now, to get the stretch, do you see what to do? How much did it stretch? Yes, 1 minus 0.883. This was the original height of it above the ground. Now it's only this far. So it's 1 minus 0.883, which is, isn't going to have one C. 0.117, is that right?
Yeah.
Okay. So you're just going to repeat that process up down to 500 grams, okay? And then, oh wait, we have force. So what we're actually measuring or calculating is the force exerted on the spring. So we need the weight, the additional weight that's hanging on here. So the additional weight is whatever the mass is in kilograms times 9.81. Okay? The mass in kilograms times the acceleration due to gravity, or times the gravitational field strength, however you want to think of that. So that's how you're getting that column. So I guess this first one would be 0.981. And everybody's going to have the same force values. Now, once again, we're ignoring the mass of the weight hanger for the first experiment, for this one. Okay, after you get this table filled out, now you're going to make a graph on Logger Pro of force versus stretch. And it ought to be a straight line. And really, it ought to pass through the origin. But remember, you're going to have points, and then you're going to do a best fit line. Oh, and you know what? I guess we want to really make that 0, so that you've actually got 0, 0 as a point on the graph. Okay? When you don't have additional mass from the weight hanger on there, the stretch is 0. And that's when the force is 0. So you could fill out that part right now. Oh, it's already there. So include that on your graph. All right? That should be a point on your graph. Okay, best fit line. The slope is, what's the slope? Can you tell me? I don't want a number. The slope is your K.